being given the keynote in a conference focused on reproducible NLP, I thought this was a great opportunity to talk a little bit about what we mean about reproducibility and why it matters. So actually, when we talk about research, we're talking about a process of systematic inquiry. So, it's not enough to find out a result. What we actually need to find out is can we search for that result and find it again and again. So actually, even the word research itself is repeated search, research. So I thought that was a very interesting, understanding that I'd like to highlight here today. So, the goal of research is really what we're trying to do is find the truth. There's a lot of noise. There's a lot that's left to chance. But can we find the true signal? The real evidence from the data again and again. So reproducibility really isn't just a box to tick. It's the very mechanism by which science becomes cumulative, and when the knowledge that we discover, can be verified by others, that they can challenge it, and then they can go and build their own extensions to that knowledge on your research. So there's a nice quote which doesn't seem to come from anyone, but I really like this phrase here. A result that cannot be reproduced is not a result, it's just an anecdote. So there's difference between something that you have had some personal experience with, maybe some observation, but until you can systematically repeat it, it's not a scientific result. So, linking that to NLP, I would say that in today's world, it's actually getting much harder to do reproducible research, because we're in an era now where we're depending upon these really complex machine learning systems, and we're going to look a little bit about why reproducibility is hard, and it's not just one problem. It's actually, there's a hierarchy of problems. So you can think of research in large language models as being kind of different layers, a hierarchy of layers of engineering and work. And if the foundations aren't reproducible, then the higher layers can't be either. And I would say that probably at the bottom of all this are tools and infrastructures that we build on. And so these are kind of the foundations, right? Because all of our experiments needs to run on software. And so these toolkits are very complex, and they're becoming more and more complex, and there's more and more interdependencies between them. Many of these toolkits are actually open source, and that's actually a fundamental plank of reproducible NLP, but it makes it very hard to reproduce research when we're not just talking about, say, one toolkit, but there are many different library versions that in each individual instantiation might have different library versions, and then it's not clear whether you've run exactly the same experiment or not. And then, of course, there's the other factor, which is that these are deployed on very big clusters of hardware. And so you have, different hardware, different library versions, and then you have a lot of non-determinism. You're not quite sure if you can reproduce the results. So at the evaluation layer, we have a whole set of other problems. So it's becoming more and more of a moving target evaluation in our field, because benchmarks get saturated very, very quickly. So they're changing versions of benchmarks. They also get very quickly pulled into training data, so there's a lot of contamination. You're not quite sure which models have been contaminated with which evaluation data. And then sometimes, we're going to talk a little bit more about today, is that the metrics that we're using don't actually perfectly match with like real actual task performance underneath. So are we even measuring the right thing? Looking at the model layer, which is probably where people focus the most, it's very, very difficult to reproduce the training of these large models. It's just completely infeasible, too costly to retrain. So you can't try different parameter settings or different data mixes, and makes it really hard to know if that setting was the right one or the same as the previous version. If you're not even planning on training models, then a lot of research is based on calls to closed models, frontier models. A lot of published research actually says, oh, on Claude or on GPT-5, whatever. And you might write down the version or the date that you called that model, but no one can call it again because these things update silently behind APIs, and so you really makes it almost impossible to know if you found a problem with Claude. By the next week they might have fixed it. So that really affects reproducibility. But then essentially, a problem that I think this crowd here today and myself have worried about was that, with models, okay, maybe people have open sourced the weights of the model, but we don't actually know exactly what the data is that it was trained on, or the hyperparameters, so you can't reproduce it. So all these problems become much sharper when you're looking at multilingual natural language processing, because low resource languages have the least amount of data, and also they have the worst evaluation infrastructure. So any kind of randomness in the setting can doubly affect experiments in other languages. And then there's also the other problem where translated benchmarks can often inflate the scores, be unreliable scores, and also they can cross-contaminate. So if the training data for the the test set for the English is somehow in the training data of the model, it can affect the German, French, and Spanish results as well. And as the field is moving, the gap between what we can kind of hold firm and pin down and what's released is becoming further and further away from what is actually necessary for others to go and reproduce those results faithfully. So the problem's becoming more and more difficult. And the question really is, all of us here, we want to make sure that we can ensure that our work remains trustworthy and reproducible. And so this is the landscape in which quite a lot of my work sits, what motivates the talk today. So I will start with some examples of open infrastructures that allow experiments to be repeated. So that's in the open tools section of the talk. And then I'll address evaluation, where we need to ensure that our metrics are actually measuring what they say they're measuring, and they can measure it reliably. And then finally, I will present some research on multilingual models that other people can inspect and reproduce and improve on. So I'll trace this journey from tools to metrics to models. So this is a very brief kind of step into history, but it's very relevant today. So our work on reproducibility goes way back. So this paper presented the toolkit called Moses, which I think fewer and fewer people here today probably remember. But this was an amazing software toolkit that was led by my supervisor, Philip Kern, who started our research group in Edinburgh. So it was released in 2007, open source toolkit that basically led the way in phrase-based statistical machine translation. So before Moses came along, every different group had their own implementation of a machine translation, statistical machine translation model. It was very hard to compare them. And so having an open source toolkit really galvanized the field and ended up with hundreds, if not thousands, of researchers building on Moses, running experiments. It was the foundation of many systems that were submitted to the conference on machine translation, shared tasks, and it really pushed the field forward and ended up being used also by many businesses, built translation businesses on top of Moses. And it really also, I think, inspired the field and future work to being, it was clear the benefits, both for us as researchers, but also for the field in general. The benefits of open source became glaringly obvious, and many other projects took that as inspiration. So as the field transitioned to neural machine translation, Nematis brought that same open science philosophy to the new paradigm. It was led by Zurich's very own Rico Senrich, but developed at our group in Edinburgh. So it was one of the very first accessible, high-quality neural machine translation systems that enabled other researchers who didn't have the resources to build from scratch to build on it and join the neural machine translation wave or tsunami. So it was written in Theano and it was widely used for a couple of years, but then the field moved on to like TensorFlow and other toolkits. It became quite hard to maintain. So we quickly followed Nematis with another toolkit called Marion. So Marion philosophy was different. It was not aimed so much at researchers, but more at production code. It was written in C++, so it was very efficient. And it was the engine behind many deployed machine translation systems, both at Microsoft, where it's delivered millions of translations a day for the last 10 years. And I think it highlights how these toolkits can really benefit both research and industry, and that can complement and reinforce each other. So it's quite interesting to look back at these open source toolkits and kind of appreciate how much they benefited our field, but also to see that actually things have changed quite a bit in the intervening time. So, there's still really powerful and important open source communities clustered around key tools in our field. So there's things like PyTorch and Nemo and VLLM, just to name a few. But what seems to be happening is that these tend to be really led by or massively influenced by very large organizations. So some of the richest companies in the world are investing, a lot of engineering time into these toolkits. So, PyTorch is led by Meta, and Nemo is led by NVIDIA. These kind of software toolkits, it's almost impossible for a research group like, say, in Edinburgh to be leading this kind of engineering effort, given the pace of change in the field and the resources that we have. So just an interesting kind of thought about, is this what we want as a field? Does Meta have our best interests at heart? Maybe not. Okay, so now I move on to the I'm not saying they're not. Just thought. Okay, so now moving on to the next layer, which is evaluation. So my contribution to reproducible evaluation runs to quite a few papers, and they all sort of address different failure modes. So why are we going to talk more about machine translation evaluation today? Well, partly because that's where I've done most of my work, but also I think that machine translation has a lot to offer the NLP field still today. And I think probably the most valuable contribution we can make is in the field of evaluation, because it has, machine translation evaluation dates back to the beginnings of the field, almost 80 years. So it's got a long and rich tradition of being very critical about evaluation. And I think what I'll talk about in the next few slides is about the fact that actually the evaluation itself needs evaluating. So it's sort of kind of a higher level kind of thinking, or not just another metric, but how reliable are these metrics? So how did we do machine translation evaluation? How did we evaluate our metrics, our blur scores, our chirf, our comet scores? These are the most common machine translation metrics. So for probably over a decade, the way we evaluated machine translation metrics was with correlation with human judgments. And this seems fine. Yes, what we want metrics to correlate with human judgments. That's obvious. But they never did. They never correlated with human judgments at the sentence level. So if you look at individual sentences and individual metric scores on individual sentences and what humans would rate individual sentences as, the correlation almost disappeared completely because of all the noise. So there was an enormous amount of human evaluation noise, and also the metrics themselves made a lot of mistakes. But the metrics did seem to correlate very well, and this is what we based our understandings on at the system level. And this, I think it's not widely enough understood, certainly for people who haven't worked heavily in machine translation, that when you talk about correlation at the system level, what we meant was, so you take a test set, 2,000 sentences of English, German, for instance, and then you run your system on it. You get 2,000 system translations out, and then you score this with human judgments and with metric judgments, and you aggregate all those scores, and you end up with one number, one score for the human evaluation and for the metric. And then you do this for 10 systems, because say you're in the conference for machine translation, you're comparing 10 systems that have been submitted to this English-German task. So you've got 10 systems, and you do this 10 times for your 10 systems, and then you rank them from best to worst, and you basically compare the ranks between the human evaluations and the metric scores. So you sort of massively aggregated all these scores into this, basically 20 numbers that and then you correlate those two rankings with each other. So you're basically hiding an enormous amount of information here. And this might be useful if you're running WMT and you're wanting to say, okay, this is the best system this year for English-German. But it's not really adequate for many, many uses. For many uses, you want to know, is this sentence a good translation? And that's really important. So one of the works I'm going to talk about was this paper called Extrinsic Evaluation of Machine Translation Metrics. And the idea of this is that it's incredibly difficult to accurately measure translation performance. So instead of doing a very hard task that's kind of almost meaningless, why not turn it into a much, much simpler task? So translations are used in many different circumstances, and you can use them as input to other systems. So for instance, in this case, an extrinsic task, an example on the slide, is for dialogue state tracking, where you're trying to extract slot fillers, for a dialogue system at the end. So in this case, dialogue state tracking is the extrinsic task, and we don't really care necessarily how good the machine translation is. We don't need some sort of score from 0 to 100 on it. What we really want is to know whether the downstream task, dialogue state tracking, ended up with the correct answer or not. Why do we want this? Because, well, firstly, it's motivated by real use cases, but secondly, we know how to evaluate dialogue state tracking. It's simple accuracy. So you could say, well, how many of the slots did it get right at the end of the day? And then we have a real number that correlates with real performance, something we actually care about. And then what you can do is you can you run the system and you've got the dialog state tracking accuracy results, and you can correlate that with different machine translation metrics. And you can see whether these machine translation metrics correlate with the dialog state tracking results. And then you can see, do they correlate? So we then evaluated a whole bunch of metrics, and we found that amazingly very sophisticated and state-of-the-art machine translation metrics that people are relying on commonly, like Comet, do not reliably distinguish translations that lead to successful completions from those that do not. So basically, the whole of evaluation of our field was built on sand, it seemed. And we had some recommendations. So what we wanted was to provide task-relevant and interpretable signals instead of just these, like, say, a number 37, to actually, for instance, go and find particular errors and label them. That was far more useful. So we took this idea of extrinsic evaluation a little bit further in this next paper, which again is collaboration with our favorite Swiss researcher, Rico Senrich. So ACEs, so the idea here is that these aggregate scores, so say a system level number evaluation, is what it's hiding is a lot of failures, a lot of systemic failures. And what we're trying to do is really try to find out about difficult kind of linguistic phenomena, like where are we failing? Where is the translation failing? So we create this data set, this challenge data set with adversarial examples that basically we know fail in particular cases. So negation, named entity, discourse coherence. And these phenomena are quite rare in the test set, so they would be completely hidden by some kind of aggregate metric. So we created this ACEs data set with a mixture of existing benchmarks and then manually create examples, and also we automatically, synthetically created examples and then validated them. And we created a very large challenge set of 36,000 examples across 146 language pairs and 68 different phenomena. And then what we did was, of course, okay, so here's a few examples so you can see more clearly. So we have like the reference sentence, for instance here, sentence A. It's an example of a case for addition. So what we did was synthetically add this word here, domestic, into the reference and created a kind of error of addition in this case, and we want to see if the metric can detect that. So here's an example of substitution and one of deletion. And because of the recommendation from the extrinsic evaluation paper, we didn't just add the errors, we also labeled them so that it could be used by metrics to see if they can actually find, not just detect it, but find where it is in the sentence. And then we took the data set and we evaluated it, a large number of metrics, all the metrics that were submitted to the Conference on Machine Translation Shared Task in 2022 and 2023. And basically we got some understanding, some sort of analysis and insight from the study of all of these different metrics. And again, what we find is that high-performing metrics that correlate well with human judgments, they often fail to detect many of these important translation accuracy errors. So these are metrics that we trust, and they look really good on standard benchmarks, but they turn out to be unreliable when you test them on these specific error types. The other conclusion was that there wasn't a particular winning metric, so all the metrics sort of failed on different ways. So it seemed like you couldn't just pick one metric and say, okay, this is really the best across all these different error types. So the idea there is possibly what you need is actually a mixture of different metrics to cover different failure cases. But I think there were sort of two very sobering findings that in fact, most metrics tend to disregard that information present in the source sentence. So is it really understanding the task properly? And then also, we thought neural metrics would overcome the problems of like string matching metrics, but actually it seems that they still heavily rely on surface level overlap, which is again a sobering conclusion. And at the end of the day, what we did, we created a reproducible challenge set for machine translation evaluation, which has been widely used in the metrics shared task in WMT. I think it's a real contribution to reproducible multilingual NLP. So there's been these 3 papers that are quite linked. You know, we've seen extrinsic evaluation asks, can metrics predict downstream task success? ACES asks, can metrics detect specific translation errors? And SPAN ACES asks, can metrics identify where errors occurred? But the same principle applies when we're actually evaluating large language models themselves. So accuracy scores can tell us whether the model gets the right answer, but you know, can we really trust it? Can we measure if the large language model is getting things consistently right? And so the next work on Monitor tries to address this question. So this is a way of measuring the reliability of our accuracy scores. So in order to understand Monitor, we've got 2 examples here showing the 2 different phenomena that we addressed. So in the top phenomena, we're looking at the prompt framing effect. So that is the fact that LLMs generate different predictions depending on how the prompts are framed. So in this case, we've got 3 different questions relating to the same underlying knowledge. So, you know, knowledge that the country is situated in Switzerland can be asked in these 3 different ways. And, you know, for some ways of asking it, you can get the right answer, but you just rephrase it or reframe it, and you get the wrong answer. So you're wanting to measure how sensitive a large language model is to these different reframings. And similarly, you're wanting to understand how sensitive the large language model is to in-context interference. With this example here, we can see that, you know, you possibly, before the questions happened, maybe people were talking about something else, some other city or other country. And if you add this as in-context information, you sort of prepend it. In many cases, the large language model can fail. I mean, this is quite a simplistic example, but it's illustrative. So what does Monitor do? What it does is it looks kind of into the model, into the bowels of the model, and it extracts the probability distributions for predicting the next word, the answer to this question. And at this point, when the model's about to produce the next word, the answer, it creates this primary anchor where it actually prepends the question with the correct answer to get the highest probability answer here. Switzerland is boosted, the probability is boosted. And then it basically compares this number with 2 other numbers. One is the prompt framing degree, so this measures the robustness to wording, so it's just the difference between the primary anchor and the probability of the correct answer in the reworded, reframed question, the one that's actually standard in the data set. And then it also compares it to the one where we've provided this in-context information, which is interference. So it ends up with these 2 different numbers, the prompt framing degree and inference relevance degree, and it combines them into this overall metric called Monitor. And what you end up with is a metric where, for Monitor, the lower is better. So a low Monitor score means that you've got low sensitivity to prompt framing and prompt interference. And then what you can do is you can compare. This is a plot for both shows accuracy and the monitor score in the blue star. And we compared a number of different language models here across the bottom, and you can see that sometimes models have very, very similar accuracy scores. So here, for instance, Vicuna and Wizard both have similar accuracy scores, but their monitor scores are very different. So this is a tool that lets you choose language models which are much more reliable. So in this case, you would prefer the one with the lower monitor score. Okay, so evaluation can take you only so far. We can detect when systems fail, but to know why maybe requires looking inside a model. And to do that, you actually need access to all the information that was used to train the model, not just the weights. So this work kind of was inspired by this question of, do the current large language models really serve Europe? So the dominant large language models are proprietary and closed, and they're very opaque. We know very little about their training data, and there's no replication paths possible for researchers. There's also a large-ish number of open weights models like Llama, Qwen, and Mistral. These are not really properly focused on Europe. Also, they don't provide a lot of information needed for replication or for true research. If you're a researcher in Europe, it's prohibitively expensive to run thorough experiments on these large frontier models. So what Europe really needs is like a basis for research and innovation that's focused on Europe's needs, Europe's languages, with full reproducibility, so full access to not just the training data, but the checkpoints, the training scripts, the evaluation code, alongside the weights. And so this inspired the EuroLLM project, which I'm going to talk about. And I know that probably some people here were involved in the PERTUS project, and it's a very similar motivation. We were very lucky last week to have Alex Hegel come to speak to us about the PERTUS project and some results. And I'd like to discuss with people more here later about the differences and advantages of each. So EuroLLM could only exist because of large compute grants. So we don't have, Google or Meta's pockets, but we do have the support of our EuroHPC and the Commission to support research and also infrastructure. So we were awarded 3 different lots of node hours. I think one thing to comment is that we started quite early on this. We were applying for compute grants in 2022 when, sort of at the beginning of this, but it takes a long time for the grants to come through. And so along the way, a lot of other people have joined in this effort. There are people in Stockholm and Sweden and in Spain and Italy working on European language models since we began. So what have we achieved so far? We started off doing some scaling experiments, and then in August 2024, we released a small model based on Instruct version, and then we released a 9B based on Instruct at the end of December 2024. So this model has had a lot of interest, particularly the Instruct model. Been downloaded many, many times. But, pretty small models, really. So we released the 22B version in June of last year. And then this year in February, we had a big release of version 2 of the 9B model, a small mixture of excerpts model, and a 22B model. And alongside that, we released the model checkpoints, and we released the pre-training data and the supervised fine-tuning data, and our also long context SFT data. So this was a snapshot of Hugging Face results from, I think, yesterday, of the number of downloads, and you can see that the smallest model has been downloaded 630,000 times, then the 9B model 367,000 times. So it's been of massive interest to researchers and potentially industry as well. And also looking at last year's WMT shared task competition, actually half of the systems that were submitted said that they had based their method and model on a EuroLLM based model. So it's also spurred quite a lot of research. Okay, so a little bit more about EuroLLM. The idea of EuroLLM was to cover all the official European languages, but also, there's quite pragmatic thinking. So, people in Europe also need to translate to and from the major global languages. So I know that Apertus covers maybe, I think, 1,800 languages. Is that true? So, what we were trying to do was we want this coverage, but we don't want to go too broad because we're wanting to prioritize performance. So we wanted, lower the number of languages somewhat, but really try to get the highest possible performance across all of them. And in order to do that, the fundamental step is to decide on what kind of size of vocabulary we want to need. So some of the open models have very large vocabularies, like Tuken and Salamandra, with a vocabulary of about 250,000 words. For EuroLLM, we wanted to go, Mistral has a very small vocabulary. We kind of chose somewhere in the middle. And when we now analyze the fertility across languages, that's the number of tokens per word on average in a corpus. And looking at different languages, what we've seen is that, so EuroLLM is the one in green on the right, that across languages it's really trying to keep the fertility as low as possible. That's probably helped with our success. So as is pretty standard in training large language models, there's a number of different phases. So we have the pre-training phase, sort of the annealing phase, and then we have a final sort of third phase with very, very high quality data. So at each phase, we're sort of reducing the learning rate, and we're also adding higher and higher quality data. I think a thing to note is that in total, EuroLLM was trained on far less data than other models, given our compute budget. So we can see the different mixes of data. So between the web data, high quality data like Wikipedia, parallel data, and code and math data. As the phases go along, obviously there's more and more high quality data and more data related to the downstream test sets, the benchmarks that we're going to use to evaluate the model. And the numbers in the graphs I'm reporting now are referring to this technical report. There were a couple of other reports with different releases, but these results come from that technical report from February. I think it was from February or March the report came out. Okay, so looking at results, how did we do? So we evaluate across quite a large number of different benchmarks, common sense, natural language understanding, maths, and then the last three here are machine translation benchmarks. So we can see that EuroLLM is the strongest model across a number of these different results. So the baseline models here are Apertus, the 70B, and Olmo 3.1, 32B. So EuroLLM was trained on less data and it has less parameters, and it's still beating much larger models And, in particular, it's consistently beating them. Well, it's beating them quite convincingly on the machine translation tasks. Okay, so, and these evaluations, I think it's important to mention, is that we used LLM as a judge with 3 very different and frontier models, instead of using rule-based methods to extract the answer to see whether the answer is correct for these accuracy benchmarks. Whereas the machine translation results were evaluated by the latest COMET metric, COMET 22. So we really applied sort of the gold standard evaluation methods for this table, this graph here. And then this graph just adds in a couple of really well-known baselines, so Mistral, Llama, Gamma, and Quen. And you can see that EuroLLM family sort of trails the very best open weights models. But it still is the strongest fully open European alternative to date. So how did EuroLLM perform so strongly against much larger models with far less training data? So this is just one quick graph showing the base model results. So all of these models, these results were on the instruct models, and this is a table showing results on the base model. So here the best results are in bold, and the second best results are underlined. So here we can see that Apertus is quite strong, although almost maybe beating it. For Hellaswag, MMLU, and Oxy. So I think we can see that, the 22B does quite a bit better than the 9B. And, just highlighting that actually, I think these results are pretty strong, considering that we had so much less data. And also smaller parameter size. So my claim is that the reason we did so well is because of the care and effort we put into the quality of the pre-training data. So, we did it. We applied all the best recipes to the data. We used educational filtering with FineWeb Edu and EuroFilter. We also applied other extensive filtering and deduplication attempts. There was a lot of high-quality parallel data included in the training. We also expanded the amount of code data and mathematical data in training with the stack, FineWeb, GSM8K, etc. And then we also generated a whole number of maths examples using frontier Quen models. Obviously, we upsampled high-quality data, and we also added quite a lot large long context data sets to support. We increased the context window to 32K for the EuroLLM 22B. And then, we released EuroWeb. You can download this from Hugging Face. We also released EuroBlocks, which is the post-training data. And here we're comparing the old versions of the 9B and 22B with the new versions, and we can see consistent improvements across, again, all these benchmarks, except for translation, where actually our performance just remains the same. So we haven't lost translation performance, but we've gained performance on maths and coding benchmarks. So the post-training recipe that we have, the EuroBlocks post-training data set, yields a significant performance gap over previous EuroLLM checkpoints. And there again, it's pretty much the same story. So, we combine multiple public instruction data sets like OpenHermes, Aya, Tulu, Nematron, with newly generated responses. So rather than just aggregating existing instruction data sets, we rebuilt the data set from scratch with frontier models, and we expanded coverage with general assistant tasks, coding, math, and STEM reasoning data sets. We also removed reasoning traces for consistent non-chain of thought supervision. So we're planning in the future to release a reasoning version of EuroLLM, but that's still coming. And so we released this data set. It's about 10.6 million multilingual instruction pair response pairs. And, you know, this is a contribution to the field and hopefully will be built upon. And these data sets are also being downloaded. Like last month, EuroBlocks was downloaded 300,000 times from Hugging Face. So hopefully a big contribution to reproducible multilingual NLP. Okay, so just got a few minutes left, and I wanted to maybe challenge the audience and maybe get feedback and discussion, if not now, but later during the day. What will it mean in the future to have reproducible NLP? So, you know, till today, we've been very carefully constructing code bases and data sets and analyzing metrics and thinking about our, you know, experimental designs. But in the future, what are we going to be doing? You know, are stable code bases going to be the foundation of research going forward? Maybe not. You know, if you can just prompt Claude and ask it to reproduce, you know, a massive engineering effort like NLP. This was a fundamental paper in machine translation from a couple of years ago and was led by Meta. It had about 40 authors and, you know, hundreds of person months or years even involved, you know, massive, massive effort. If, you know, we can go off and just prompt Claude one day, sitting in our sitting room, to reproduce this result. Obviously, you'd need the compute as well. So basically what I'm trying to say is that the code is no longer fixed. It's something that sort of emerges as you interact with an assistant, an AI assistant. You know, that might be all very well. And maybe, you know, we can come up with advances and improvements quicker and try out ideas faster. But will people be able to analyze them, examine them, verify them, and build upon them is the question. So to finalize, research is literally the act of searching again. So every scientific claim is an invitation to someone else to look at it and examine it and see if they find the same thing. And you know, open models or releasing weights is definitely necessary, but it's not sufficient. And you know, reproducibility doesn't just happen. It happens because all of us here are engaged in it and we care about it. And so, you know, please keep releasing your models and your code and, you know, keep evaluating carefully and honestly and challenging yourself and not just relying on metric numbers. Thank you very much.
Thank you, Alexandra, for this nice talk. I think we're already running into the coffee break, but I still want to give people the opportunity to ask a question or two.
Many thanks, Alexandra, for this interesting talk. I fully subscribe to your call for more conscious evaluation. And what I wonder about is, like, I know that Claude is a super strong model, even though I'm a little ashamed to say I've never used it personally, and I haven't looked at any evaluation results of it. I know this because my colleagues say to me, hey, this is a good model, and I see them cranking out a code base in no time, which, like, surprisingly works extremely well. And so there's this kind of new feedback that you can gather. It's, I call it like community feedback. And I saw your models have been downloaded tons of times, so I wonder if you get some feedback from this tons of downloads on the quality of the different models that you released?
So I guess large language models are evaluated kind of anecdotally a lot. I mean, there's not just your own personal impressions of it, but, you know, journalists write blog posts and they say, hey, it fails in this case, you know, or Gary Marcus will criticize, you know, GPT or something with some unusual kind of adversarial prompt that he's come up with. We did get some community feedback about Polish. Apparently wasn't very good in Polish, the first version. I'm not quite sure why. There's Polish is quite well. Maybe it's just very hard. That kind of feedback isn't very useful for us because, I mean, we certainly go and look at the data and make sure there wasn't some error with our Polish pre-training data, for instance. But, you know, these engineering efforts take sort of 6 months to a year. You know, you're relying on your HPC and allocating you huge amounts of compute and the next supercompute cluster. So you can't just go and quickly fix things. Yeah, I think other community feedback we got was that our 4,000 token length context was, you know, derisory and completely unusable. So that we extended it to 32K, which is kind of the limits of what we can do with the compute we have. Like clearly 120K would be, or 30K would be much better. I think Apertus has 130K context length for their system, but it's really, really expensive to do that training. So yes, I think anecdotal feedback is valuable and we certainly pay attention. Please, if you're using EuroLLM and have any problems with it, let us know. But whether we can fix it or not is another matter. I mean, we're not, you know, a large group of extremely well-paid engineers in Google. Like we're, you know, a couple of postdocs, a couple of academics, and some very hardworking students.
Thank you.
Maybe if I can ask a related question. I mean, training such a large language model is always a learning experience. I think in Apertus we also learn things. I think version 1 had a good pre-training, maybe the post-training needed more work. Are there lessons you can share with the ongoing work for Apertus of some lessons you learned working on EuroLLM, some mistakes that you want to warn us not to repeat?
I think, you know, my takeaway has been data, 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 data. So, you know, clean it, filter it, generate it with the best possible models, you know, get multiple judges to vote about which is the best answer. That really pays off. But I guess what you could do is just download EuroBlocks. But obviously, if you can train on more data, then you'll need to maybe put that effort in to all that extra data. You seem to have unlimited compute here in Switzerland. I'm quite jealous. Use it wisely. It's very difficult, as also from a project management perspective, to get people to donate their times, because is it research? I don't know. It's more engineering, and people need to publish and graduate. So, you know, keeping people herded together and focused on the goal is really tough. I might think that maybe you've chosen too many languages to cover, possibly. I quite like your goldfish bowl training last. That was quite interesting. So you can make claims about it being more compliant in privacy and data and AI, EU AI Act and stuff. So yeah, they're different projects, both valuable, and there's space for all of us, I think.
Right, in the interest of the coffee break, let's thank Alexandra again. And I'm sure she'll be around for coffee if you have more questions.